What if an AI could actually stop a harmful drug reaction before it even starts? Today, we're going to dive into a pretty groundbreaking research paper that lays out the blueprint for exactly that. This is a really fascinating look at the future of patient safety. Okay, so to get why this research is so critical, we really have to talk about this scale of the problem. This number you're looking at right here, somewhere between $30 and $50 million. That's the estimated cost of preventable drug-related harm every single year for just one 500-bed hospital. It's an absolutely staggering figure that isn't just about money, it's about immense patient suffering. And that right there brings us to the core question that's driving all of this research. What if we could build a system that's smart enough to see these events coming and give doctors a real chance to intervene? That's the powerful promise we're going to explore today. So here's our game plan. First, we're going to get a handle on just how big this problem is. Then, we'll unpack the paper's brilliant blueprint for an AI solution. We're going to look at how the AI's brain is actually built, find out what it takes to make it trustworthy for doctors, and finally, see the incredible real-world impact this whole thing could have. All right, let's start with the problem itself. These things called adverse drug events, or ADEs, they are one of the top causes of preventable harm in hospitals. And we're not talking about a small issue here. This is a massive, nationwide problem that causes a significant number of patient deaths and carries an economic burden in the tens of billions of dollars every single year. So the real issue is that our current safety systems just weren't designed for the crazy complexity of modern medicine. They're kind of like simple checklists that operate on really rigid rules. They can't connect the dots between a patient's unique history, their latest lab results, and the half-dozen medications they might be on. They lack what the researchers call semantic depth, which is really the ability to understand the story the data's telling, not just the individual little facts. So to solve this, the paper lays out a master plan. It's this comprehensive four-phase framework to build, train, and deploy a next-generation AI system that's designed from the ground up for this specific purpose. And this slide lays out the whole plan beautifully. It all starts with a solid data foundation, getting all the clinical data into a language the AI can actually understand. Next up, they build the knowledge graph. That's the AI's brain, which connects all the dots between patients, drugs, and symptoms. Then comes the really crucial part, creating a trustworthy AI, making sure it's explainable and fair. And finally, clinical validation, where the system gets tested and proven in a real-world hospital. This is going to be our roadmap. So how in the world do you actually build a brain for an AI? Well, the process starts by totally shifting from just storing data to creating a system that truly understands the relationships between all those data points. Okay, at the very heart of this system is something called a knowledge graph. Honestly, the best way to think about it is like a detective's corkboard, the one covered in photos and notes and pieces of string connecting everything. It's not just a list of facts, it's a living map that connects every single clue. This patient, this drug, that lab result, this potential side effect, and it shows how they're all tangled together. Now, what's really fascinating about this slide is the huge shift in thinking it represents. See, old databases can tell you what happened. A knowledge graph, on the other hand, can start to figure out why it happened. It can guess where the missing links are and see connections in messy, incomplete clinical data that a traditional system would just completely miss. So, if the knowledge graph is the brain, then a graph neural network, or a GNN, is kind of like the consciousness that brings that brain to life. Think of it as this specialized AI that is constantly patrolling that corkboard of connections we just talked about. It's specifically designed to spot these incredibly subtle patterns and relationships that a human, or any other type of AI for that matter, would probably miss. Patterns that could be the first warning sign of a bad reaction. But here's the reality check. You can have the most accurate AI on the planet, but if doctors don't trust it, it's completely useless. So this next phase is maybe the most important of all. How do you turn a black box into a trusted clinical partner? And yeah, this is the central challenge, right? A doctor isn't just going to change a patient's medication because some computer screen tells them to. They need to understand the AI's reasoning. They need to be able to look under the hood. To get around this, the researchers built trust on three key pillars. First, there's explainability, so the AI can actually answer, hey, why did you make that prediction? By pointing to the exact lab value or medication. Second, actionability, so it doesn't just sound an alarm, it answers, okay, what should I do about it? By suggesting a specific minimal change. And third, fairness, which makes sure the system protects every single patient equally, no matter who they are. And they really go deep on this fairness thing. Instead of taking a simple approach that could actually hide biases, they use a much more sophisticated metric called equalized odds. What this does is it ensures the accuracy of the AI is consistent across different groups of people, which is absolutely critical in healthcare where baseline risks can be really different. So, we have a smart, trustworthy AI. Now for the final and most crucial step, proving it actually works in the real world. And let me tell you, the projected results are, well, they're pretty remarkable. The big headline number is this. The system is projected to reduce preventable adverse drug events by an incredible 25 to 35%. I mean, that is a massive leap forward in patient safety. And how does it do it? Basically, by seeing the future. The AI gives a median advance warning of 8 to 12 hours before a patient even shows any clinical signs of a problem. That gives doctors a huge window to step in and prevent harm before it happens. The system is also unbelievably fast. It can spit out a real-time risk score for any patient in under 50 milliseconds, which means it can slide right into a fast-paced hospital workflow without slowing anyone down. And this brings us right back to where we started, back to the economics. The savings are so significant that a hospital could see a full return on their investment in less than 6 months. It's not just a powerful clinical case, it's a powerful financial one too. So if you take one thing away from all the tech talk, let it be this. The real innovation here is the fusion of two super powerful AI ideas. It combines the why, that relational reasoning of knowledge graphs, with the what, the pattern spotting power of graph neural networks, and it wraps it all up in a system that's built for the pressures of the real world. And all of this leaves us with a pretty powerful question for the future. This research gives us a clear blueprint. So as this technology gets tested, refined, and rolled out, are we watching the birth of a new standard of care? A future where every single patient is watched over by a dedicated AI co-pilot, making medicine fundamentally safer for all of us?